Hello students, today we'll continue again with unit number 4 and this is the last topic, topic number 7, which is descriptive studies on dams, weirs, barrage, head regulator and silt excluder. So first one is dams. A dam is a barrier that impounds water or underground streams. Reservoirs created by dams not only suppress floods but also provide water for such activities as irrigation, human consumption, industrial use, aquaculture, and navigability. Hydropower is often used in conjunction with dams to generate electricity. So, in dams, we get two parts, that is catchment and reservoir. For catchment, the collection of rainwater over a natural drainage area during rainfall is better known as catchment. Then a reservoir usually means an enlarged natural or artificial lake, storage pond, or impoundment created using a dam or lock to store water. Reason for dam construction. Why do we construct dam? The first one is flood control, second is agricultural purposes, third is hydroelectricity, fourth is water reservation. What are the different dam site requirement criteria? The first one is area having gentle slope rather than steep slope, that is slope stability. Area receiving adequate rainfall, area away from settlement and agricultural fields, permeability of soil or type of soil, water table, effects on forest and wildlife, earthquake faults and stream flow or watershed. The second topic is weirs. So, what is a weir? A weir is a structure constructed across the river to raise its water level and divert the ether into the canal. On the crest of the weirs, usually shutters are provided so that part of the raising up of water is carried out by shutters. During floods, the shutters may be dropped down to allow water to flow over the crest of the weir. Weir is usually aligned at right angles to the direction of flow of the river. Weirs may be classified according to the material of construction and certain design features into the following three types. The first one is masonry weirs with vertical drop or vertical drop wires, rock fill weirs with sloping aprons, and concrete weirs with a downstream glacis or glacier. Types of weir depending upon the floor design criteria. The first one is gravity weir. It means uplift pressure is resisted entirely by weight of what? Next is non-gravity weir, which is uplift pressure is resisted by bending action of reinforced concrete floor. Next, types of weir depending upon the materials used. The first one is masonry weir with vertical drop. So this type of weir consists of a masonry wall with either both upstream and downstream faces vertical or both faces inclined or only upstream face inclined. It has an impervious horizontal floor or apron. Cut-off walls are provided at both upstream and downstream ends of the floor as shown in the figure. Next, rockfill weir with sloping apron. So this type of weir consists of a masonry wall and dry packed boulder laid in the form of slope, that is 1:20 at downstream and 1:4 at upstream, with weir wall at middle and few intervening core walls. The downstream slope is generally made very flat. It requires very large quantity of stone and would be economical only where stone is available in abundance in close proximity. The third one is concrete weir with downstream glacis. In this type of weir, sheet piles of sufficient depth are provided at upstream and downstream ends of the floor as shown in figure. Intermediate piles are also provided in some cases. Its design is based on modern concept of subsoil flow, that is Kosla's theory. You can refer to Kosla's theory later. So this type of weir is constructed on pervious foundation. Next, barrage. In the case of a barrage, the crest is kept at a low level and the raising upper water level or ponding is accomplished mainly by means of gates. So during floods, these gates can be raised clear of the high flood level and thus enable the high flood to pass with minimum of efflux or heading upper water on the upstream side. A barrage provides better control on the water level in the river, but it is comparatively costly. Next, head regulator. A canal head regulator is provided at the end of each main canal of taking from diversion headward. It should be so aligned that its axis makes an angle of 90 degree to 120 degree with the axis of weir as shown. So functions of canal head regulator. The first one is it regulates the supply of water into canal. Second is it controls the entry of silt into canal. Third is it prevents the river flood from entering the canal. So it can be used to stop the canal supply when the silt in the river water exceeds a certain limit. Next, silt excluder. So silt excluder is a structure constructed in the bed of the river upstream of head regulator to attack the river bed water and divert the same into the downstream of the river. Its main function is to prevent the entry of silt into the canal. So they are also called as silt extractors and are provided to extract silt from canal water after the silted water has traveled a certain distance in the off-taking canal. These works are therefore constructed on the bed of the canal and a little distance downstream from the head regulator. They consist of curved tunnels located across the canal which starts along the axis of the canal and turn towards the bank into the escape channel. The silted water is discharged into the downstream side of the river from the weir. So this is your assignment for lecture number 32. The question is you have to explain in detail about barrage, head regulator and silt excluder. I repeat, you have to explain in detail about barrage, head regulator and silt excluder. So the last date of submission is already mentioned here. Also at the same time, now you can give your attendance in the chat box. And now we'll go through a video. Just watch it. And related to that, those videos, I'll be giving you assignments in the upcoming classes. So just go through the video, okay? That's all for this lecture. Thank you.
able to control the level of water in a river is beneficial in quite a few ways. Historically, mills relied on water power to drive saws, grinding wheels, and other equipment. Raising the water level in a river can also allow boats and ships to navigate areas that would otherwise be inaccessible. Finally, having control of a river can help mitigate the damaging impacts of flooding. But how do we get this type of control over the level in a body of water? Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about weirs. This video is sponsored by Skillshare, the best way to learn a new skill online. More on that later. A weir is a small dam built across a river to control the upstream water level. Weirs have been used for ages to control the flow of water in streams, rivers, and other water bodies. Unlike large dams, which create reservoirs, the goal of building a weir across a river isn't to create storage, but only to gain some control over the water level. Over time, the term weir has taken on a more general definition in engineering to apply to any hydraulic control structure that allows water to flow over its top, often called its crest. In fact, the spillways of many large dams use weirs as control structures. So how do they work? If you watch my previous video on the basics of open channel hydraulics, you'll remember that for subcritical flow, that is, slow, tranquil flow seen in most rivers, the depth is controlled by downstream conditions. That means adding a weir across a river will increase the water level upstream. But by how much depends on the flow. This is the equation for flow over a weir. We're not going to do any calculations here, but it's important to know the factors that govern the performance of our hydraulic structure. This equation says that the amount of flow that passes over a weir depends on three factors: the length of the weir, the height of the water level above the crest of the weir, and this coefficient which changes depending on the geometry of the weir. The graph of a hydraulic structure's flow versus water level is called its rating curve, and this is the rating curve for a typical weir. In many cases, a weir is a passive structure, meaning that once it's installed, there's no way to change this rating curve, and that's not always ideal. Streams and rivers are subject to tremendous variability in flow rate. A hydraulic structure may normally flow a small amount, but in flooding conditions be asked to pass incredible volumes of water. With a passive structure and fixed rating curve, that variability in flow means tremendous variability in the water level upstream. During a flood, a weir may back up water badly enough to cause damage upstream. If you're using a weir for a spillway on a dam, you might have to build your dam much higher just to handle the water level that occurs during very rare but extreme cases, increasing the overall cost of the structure. Ideally, hydraulic structures used to control water level would have a flat rating curve, meaning over a wide range of flows you only get small changes in level. So how could we flatten this curve? Going back to the Weir equation, there are only two other parameters available to increase the flow for a given water surface. We can improve the geometry of the weir to increase its efficiency. Different shapes of weirs can pass flow more efficiently and thus have a higher discharge coefficient, but this has a practical limit. The most efficient shape for a weir is to match the curve that the water would take off a sharp crest. This part of the flow is called the weir's nap, and the shape that matches it is called an ogee. With ogee-crested weirs, we can get discharge coefficients as high as around 4, but that's pretty much the limit. The other parameter we can change is the length of the weir, but in many locations, the available footprint for the weir is a fixed size that can't be increased. Even if the footprint isn't fixed, increasing the length of the weir can add significant costs. Of course, this challenge is easy to address if we allow for structures with moving parts. Many dams and spillways have large gates or valves to control flow. There are a wide variety of types of controlled outlets used on hydraulic structures, including crest gates that act like weirs that can be raised or lowered. The benefit is that the structure's capacity can be increased while flows are high by opening gates, and then decreased when flows return back to normal. Controlled structures provide more flexibility in how water gets released or held back, essentially turning a static rating curve into a family of curves that can be selected from to meet operational goals. Of course, controlled outlets come with a major disadvantage of increased complexity, and in many cases, requiring an actual person be available 24/7 to open gates and make releases based on inflows. So what if we could get the benefit of a controlled outlet without the disadvantages of increased complexity and operational obligation? Well, there's one more trick that hydraulic engineers have up their sleeves. Remember when before I said you could only fit a certain length of weir within a fixed footprint? That's not completely true. We can actually fold a weir to get more length within a given space. This is called a non-linear weir, and it's used in situations where you want greater discharge within a given footprint, but without the need for actively controlled outlets. To show how this works, I built this flume and some model weirs. This first weir just goes directly across the flume with no bends. I'll mark the water level in the flume, first using the straight weir. Now, with the same flow rate, I'll replace the linear weir with the folded version. This has just about twice as much weir length in the same footprint. You can see that even though the weir is passing the same amount of flow, the water level upstream is lower, almost half the distance to the crest from the original level. We flatten the rating curve, allowing for greater discharge at a lower water level. Nonlinear weirs with folded cycles like this are called labyrinth weirs, and they're becoming more common as hydraulic control structures. There are also rectangular versions called piano key weirs. It's easy to see how beneficial weirs can be, from generating power to improving navigation, controlling flooding, and even acting as the spillways of dams. But with all those benefits, there are some downsides as well. Impoundments across rivers affect the aquatic environment. Low-head dams can also pose a serious danger to swimmers and boaters, a topic I'd like to discuss in the future. In fact, many old weirs that are no longer needed are being replaced or completely removed to restore the river to its natural state. But as long as we need to control the flow of water in our constructed environment, weirs will continue to be an important tool for a hydraulic engineer. Thank you for watching, and let me know what you think.
Grammarly.
Understand the difference between dam, barrage, and weir. We often fail to notice the difference between these three words. Even though all these three are water storage structures, they have a difference. Let's go through it. Dam, first of all. Dam is a heavy water storage structure which is often constructed with concrete or rock fill. The water in the reservoir rises up to several hundred feet above the soil strata, mainly because of the structure. And here the water does not overflow. When water gets excess, it moves through a spillway. Here you can observe the difference between the level of water on the upstream side and downstream side. Coming to barrage. Barrage is also a water storage structure which stores up the water up to a few feet height, mainly because of the gates, not because of the structure. And the major purpose of the barrage is to divert the water for irrigation purposes. Coming to weir. Weir is also a water storage structure which stores water up to very few feet height. When water gets excess on the upstream side, it overflows the weir. These don't have a gate mechanism. Here you can observe the water is flowing from upstream side to downstream side. There is no gate mechanism. Let us recollect the differences. Dam is a heavy hydraulic structure where the water is raised up to several hundred feet in the reservoir and water does not overflow. In the barrage, the water storage is very few feet height and it is also because of the gates. And this is mainly a diversion structure, whereas in the weir, this water raised is very few feet height, but the water overflows the weir. Thank you for watching this video. If you like this video, please hit like button. And for more civil related videos, you can subscribe my channel. Engineering has civil engineer. In fact,